Hey, what's up everyone? Jason Turley here, back with another video. And I just sat here for about 30 minutes and talked about the video and realized I never even pressed record. So I was just sitting here, talking to myself, and all that footage is gone. But whatever, I still want to address this video because I think it'll be really cool, and we'll look at different ways of compilation and finding a hard to spot bug in this C source code file. So here I have Twitter pulled up. I was eating dinner and just scrolling Twitter on my phone, and I saw this tweet from Ivan Fratrick, and it simply states, "Can you spot the bug? The goal is to leak the secret." And if we scroll down, we see he actually includes a screenshot or a PNG of the code. We can see here that it's a C++ file. Just, you can tell by the libraries that it's including and whatnot. So this is probably one of the worst ways to actually look at code. It's not very pretty. There's no syntax highlighting. There's no colors or anything like that. So what I've done is actually typed the code by hand, and I just named it vuln.cpp, and I made my own secret.txt file. So let's actually cat out secret.txt, and it just says please sub. If I do a word count on it, we see it only has 7 letters in it, 7 characters. So let's open up vuln.cpp. I'm just going to use vim, and I did edit it a little bit. There are some printf statements here that I've commented out for now. You can safely ignore that. We see here at the top that it includes standard input output.h as well as iostream. There's not really a reason to mix the C standard library and the C++ standard library, in my opinion. Why not just use the C++ standard library? But whatever. So we see here 2 macros are being defined, size and size2, which are both 8 bytes, or they both store the number 8, right? So the size of the array can be 8 bytes long. And we see here there is a function, an inline function. That tidbit, that point will make a lot of sense later, and that will be a crucial factor into the vulnerability later. But we see it is a function called getElementSafe. It takes 2 parameters, an array of unsigned integers, and then an unsigned integer called index. And then it will return an unsigned integer pointer. So first it checks if the integer that we supply, if the index that we give it, is outside of the array's bounds, right? If it's greater than or equal to size, because arrays in C and C++ start at index 0. So if our array is of size 8, the first element will be at index 0, and the last element will be at index 7. Anything above that, 8 and beyond, will be outside the bounds of the array, and that's how we kind of can lead to out-of-bound read, out-of-bound write, buffer overflow. We've seen that time and time again on this channel. So if we do enter something that's outside of that range, it will return a null pointer, which isn't great. But if we do get it inside of that width, inside of that range, it will return an offset into that array. So here, array is just the address of the first element, and then we're adding some type of offset, in this case, the variable index, so we can get the actual element that we need. We see here the main function. We're defining the array and secret. They're both just arrays of unsigned integers. An unsigned integer is simply a positive number, so it cannot go below 0. If we input something like -1, it won't be -1. It will actually wrap around and be the largest value of an unsigned integer, which is like 4 billion or something like that. So it can only be positive. That's what an unsigned number or unsigned integer is. It can only be positive. And then I have this commented out, but we can actually print out the starting address of the array and the secret. So let's do that. And then there's going to be a for loop, simply just to initialize our array. It's not going to be all 0 by default because this is C and C++. It'll be whatever is on the stack currently. And if there's nothing on the stack, sure, maybe it's 0, or maybe it's junk or garbage. So we're initializing this array. Every element in the array will be equal to I. So I is going to iterate. It's going to go from 0 to 1, 2, 3, 4, 5, 6, 7. And that's going to be the contents of that buffer. And then here we open up a file called secret.txt in read mode, and it can accept binary format. We store that in our buffer. And then we close that handle to the file pointer. And then down here, it simply asks us to enter in our own value for the index. cin just means console in or console input. It's waiting, it's going to hang, kind of like scanf or anything like that. It's just going to hang and wait and prompt us to enter a number. After we enter our number, it's going to call this inline function, getElementSafe, with the starting address of our array, and then some type of offset or index into the array. And then finally, it's going to print it out. This star here, this asterisk in front of the variable element, means dereference it. Here's a valid address, or here's an address. Go to what lives at that address and print that value, right? So if we enter the first, if we enter index 0, we're expecting to dereference our array and get the element that's stored there, which is 0. But what if we enter something that is too large, right? If we enter something like index 8, 9, 10, then it will return a null pointer. What's wrong with dereferencing a null pointer, you may ask? So we're saying go to this address and grab the value stored there. But if it's a null pointer, which is going to be all zeros, that's an invalid address. There won't be anything stored there. We're going to be accessing some region of memory that we're not allowed to. We can't. So we're going to get something called a segmentation fault or a seg fault. So let's actually compile this code and run it and play around with it and see what it's going to do. So I'm going to use GCC, or the C++ version of that, G++, just because that's like, I guess, the compiler that I like to use. We're going to give it vuln.cpp. We're going to output it as vuln. If I do file on vuln, we see it successfully made a 64-bit elf executable. We hit enter, and I added these prompts to just print out the starting address of array and the starting address of secret. And we can see here that they're about hex 20 bytes apart. So how much is hex 20? Oh, hex 20, 32. So these are 32 bytes apart from one another, which makes sense, right? These are arrays that store 8 elements, and each element is 4 bytes long, because that's how long unsigned integer is. That's the size of it. So 4 times 8 is 32. So that makes sense. So if we're going to start reading from the base address of here, if we can add 32 bytes onto that, or 8 bytes onto that, right? We're going to start reading from the secret buffer. But we saw that check earlier, right? We saw this check of index greater than equal to size. So if we do enter anything greater than 8, we're going to get a segmentation fault. So how can we get around that? Let's keep playing. And if you want, you can follow along and try to figure it out on your own. But it is a little bit of like I guess a trick or a niche kind of bug. And it will depend on what tools you're using to not spoil anything. It will depend on what tool you are using. So let's enter 0. And we get element 0. Same thing for 1. What happens if I try to do something like index 8? I get a segmentation fault. Okay, what if I do -1, segmentation fault, 99999, segmentation fault. Okay, so there's no easy way to read outside the bounds of that buffer. Not yet, at least. So what can we do here? So I tossed and toiled and troubleshot this a little bit. So inline function, what is an inline function, you might ask? It's telling the compiler that, hey, you can optimize this away. If this function isn't doing very much, you can just expand it, get rid of it, and just use it inline. So let's actually try to find a decent article that explains that better than I ever can. Inline functions in C++. So in C++, a function can be specified as inline to reduce the function call overload. So we know when a function is being called from like a reverse engineering and CTF exercises, when a function is called, it's going to set up a whole stack frame. It's going to allocate space on the stack. It's going to tear the stack down, or the stack frame down at the end. And it's going to allocate all this stuff. And that takes a little bit of time. It's extra assembly instructions. Here, it doesn't really matter, but what if this was like a real-time operating system, right? What if this was like a medical device or a self-driving car or something that needs to be as fast as possible, where every instruction, every CPU cycle matters. So that's kind of where inline functions kind of shine in like very low level programming for things like embedded systems and IoT systems like that, where milliseconds do matter and they do add up. So that's when you might want to use an inline function. But let's read on to see more of what they do. The whole code of the inline function is inserted or substituted at the point of its call during the compilation instead of using a normal function call mechanism. So in this example, there's the inline function called square, which simply takes an integer as a parameter and it's going to return the square of that. So the integer times itself, x times x in this case. So if we enter the number 5 and we call square on it, it's going to return 25. But if we declare it as inline, here, does this actually show us what it will look like? Scroll down. I was hoping they had like an actual example of what the code would look like after it is inlined. No, I don't see an actual like example of what the inline code would look like at like the assembly level, but essentially it won't call this function. It won't call square. Instead, it will just put x times x here. So it'll just be num times num. So int result equals num times num or x times x, and it won't actually do a function call. So I was hoping we'd actually see that here in this little blog, or maybe here it is. Maybe, I don't know, there's a bunch of typos in this. But anyway, that's the kind of the point of inline functions. They're an optimization technique. And I'm curious if we'll see it when we pre-process the code, or if that is just something that the compiler will handle for us. So we can actually look at the man page for GCC and search for preprocessor, because compilers do a lot of magic, but they actually work in stages. The first stage, the preprocessor will come through and strip and expand all of those inclusions that we give. It'll expand those define statements. So we said define size 8. So it'll go through and everywhere that we use that macro size, it will replace it with the number 8. So we can see here, when you invoke GCC normally, the GNU C compiler normally, it normally does the preprocessing, compilation, assembly, and linking. So if you're like a fresh college grad and you're trying to interview for a software engineering or programming position, maybe they'll ask you something about the different stages of compilation. I don't know. I'm not an actual programmer. But now you are equipped and armed with the correct answer. Compilation takes there's 4 steps, 4 stages when you compile a C binary or C++ binary. So the preprocessor will come through and expand all of the macros in the inclusion guards, but I don't know if it'll do the same for inline functions, or is that will be later on for the assembler or maybe the linker. Probably not the linker. I think that will either be the compiler or the assembler that actually does that. But let's see how we can look at the output of the preprocessed code. Okay, so there's a TAC capital E. Stop after the preprocessing stage. Do not run the compiler proper. The output is in the format of preprocessed source code, which is sent to standard output. And then above it, we can see some other flags. TAC C, compile or assemble the source files, but do not link it. The linking stage simply is not done. The ultimate output is in the form of an object file. Okay, by default, the object file is a source file, blah, blah, blah. TAC S, stop after the compilation stage. So let's try both of these. Let's try TAC E to see the preprocessor work, and let's do TAC S. I think that's a capital S. The stop after the compiler does its magic, but don't actually assemble it. So let's come over here. Let's say G++ TAC E on vuln.cpp, and let's make the output just vuln.pre. I'm not really sure what the correct file extension should be here, or does it really matter? So I do the file command here. We can see that it is C source code. It's ASCII text. So something I can easily open up inside of Vim. And we see here at the very top of the file, vuln.cpp is in all quotes. And we see some other things that look kind of interesting. We see built-in, command line, predef.h. Here's that standard input output.h that we saw. If I search, we can probably see IOStream. So what is it doing? We told it here to include these different standard library files. So we can do things like printf and fread and fclose. We didn't define those functions ourselves. They're functions that we're borrowing or copying from these different standard libraries, right? So the preprocessor, the compiler, is going to come through and grab all that code and shove it here. So if I exit out of this real quick, if I do a word count tech line on vuln.cpp, it's only 35 lines. If I do the same thing on the preprocess file, it's now over 3,200, right? Or 32,000. It's well over 32,000 lines of code, because everything has been dumped from those inclusion headers and just thrown into our preprocessed file. So we can just hit page down and we can kind of look through here. We see the different types that are being defined and so on and so forth. If I go to the very bottom of the file, that's where we'll see our main code. And we see here, it says if index is greater than or equal to 8. Before that had the macro, right? It had size in all caps, but now it's 8. And the same thing here when our arrays are being defined, right? Instead of size and size 2, those now say 8. And we also see here, our inline function is still there. It hasn't been optimized away or anything like that in any way, shape, or form. So it will still do this function call. But let me close out of here and do the same thing with capital S, vuln.cpp, and output vuln.s. I'm not really sure what the file extension should be here. So file vuln.s, we see it's assembler code. ASCII text, and we can open this up and we can kind of look through here. And there might be a way to change the syntax of this. Right now we see that the syntax is in the inferior ATT syntax, and it's very ugly and has these parentheses and whatnot. So let me actually see if I can change that output. I don't know if it's tech M or what, but let's search for arch. I think it's tech M arch. So let's try this again. Tech M arch equals Intel. It doesn't like that. Let's just search for Intel.
2,000 years later.
Oh, here we go. MASM, so M assembly. So output assembly instructions using selected dialect. Also affects which dialect is used for basic assembly, support choices, in dialect order or AT&T or Intel. So let's quit out of this. Tech M ASM equals Intel. Now let's open that up. And to me, at least, this assembly looks a heck of a lot better. It looks way cleaner. So we can see some labels here. We see .file is vuln.cpp, Intel syntax, perfect. And we see here Z16 get element safe. Get element safe. So the function is not being optimized away. And if we scroll down a little bit, we still should see the call to it. Do we see where that function, where's it at? Get element. Right here. Right here, we can see the compare. It's comparing our input parameter. So in x64, when you call a function, the first argument is going to be stored in RDI, and the second parameter is going to be stored in RSI or ESI. So the first argument will be in the RDI or ESI or EDI register, and the second one will be inside of ESI. So this is just ASCII. So let me actually kind of make some comments. So this is the first parameter, argument, whatever you want to call it. So this is the array, and this is the second parameter, which is index, right? So it's looking at the index and it's comparing it with the value 7. And if it is below 7, so if it's like, between 0 and 7, we're good. So it's going to jump to label 2. And we see label 2 here. This is actually going to do the arithmetic. It's going to do array plus index. We see that right here, actually. This is where it's doing it. This is the addition, array plus index. And then it's going to return it down here. However, if we enter an index that is greater than 7, like 8, 9, 10, what have you, it's going to go to label. It's not going to do this jump. It's not going to do this branch. It's going to store the return value inside EAX, which is 0, which is the null pointer, and it's going to jump to label 3. So it's going to jump down here, and it's going to do the return, and it's going to tear down the stack. And then we can see here, oh, this is cool. We can see the strings. We can see the print statement that we want. We can see secret.txt and element. So this is really cool. So this is the assembly instructions, right? If you're used to doing any reverse engineering or debugging or disassembling, and you're very comfortable looking at assembly, I could have just given you this and you could have found the vulnerability. So let's exit out of this. So I know I kind of go on tangents here and there, but the main thing I wanted to drive home is looking at this inline function, and we see this comparison check. So let's close out of here and let's do the same thing, but now I'm going to add an optimization flag. Let's say O3 to do the highest level of optimization and get rid of any redundant or useless code. Hey, you're the compiler, you do all the magic. Do you see any way you can optimize my code for me and kind of make it less, I guess, spaghetti code? And this can come into play in real world programming. This is something you might want to do. Maybe it's something you don't want to do. It depends on your use case and what you're programming for. And we see it actually added additional warnings. It added warning unused result. So we called fread, which does return a value, right? It returns the size type. It returns the number of bytes successfully read, which is useful for error checking. Our secret.txt is 7 bytes in length. But what if for whatever reason we only read like 1 byte or we read no bytes? So the return value can be used for error checking and it's saying, hey, you're not actually using that return value. Are you sure you know what you're doing? I'm not going to stop you from compiling. I'm just going to give you a warning. And just like I guess a tidbit, if you want all warnings to be errors, you can just do tac W, capital W, and then error. So turn all warnings into errors, and now our code won't actually compile. We see here all warnings being treated as errors. So let's actually get rid of that flag so we can assemble our code. And let's look at side vuln.s. And do we still see that get function? We don't see get anymore. Is it still doing that comparison? Yeah, okay. So we see that inline function is gone, or maybe it's just renamed. We still see this function call here, and we still see this comparison to the value 7. So it's still checking our input. It's still checking the bounds of our input. Maybe it renamed our function or got rid of it, or maybe it is inline and is doing the checks inline as well. So let's close out of this. And I'm actually going to rename this. I'm going to move it from vuln.s to vulngcc.s. And that's simply because there's a different compiler we can use. We're using GCC or G++, but we can also use Clang or Clang++ for C++ code. So let's do the exact same thing. I'm just going to hit up arrow a few times, and I'm going to change this here from Clang or from G++ to Clang++. And just for my sake, I'm going to rename this from vuln.s to vuln clang.s, so I know that there is some type of difference. And if we do a listing on it, we see the file size is way different, right? Clang outputted way more assembly instructions than GCC. So if code size is something you care about, that might be something to look into. So let's open up the clang.s file, clang, and let's search for that get element function, pattern not found. Let's search for comparisons, pattern not found. What's going on? Let's actually scroll down to where it will be doing that array arithmetic. Okay, we see a call to printf. Where are we? We see a call here. Okay, so we see a call to fread, and we see a call to fclose. So around here is where it should be doing that arithmetic, where it should be doing that math. We can see here this very ugly function call, extract I JEERSIRT. I have no clue what that means, but we don't see any type of comparison here, right? If I do tab E, and then I open up Vuln GCC, and we scroll down, or we search for like compare, we can see the comparison is right here. But when I go to the other tab, how do I go to the next tab? Colon tab prev. There we go. So there is no compare instruction. So for whatever reason, Clang and GCC are optimizing these two functions differently. GCC is keeping inside that comparison, whereas Clang is getting rid of it. It's optimizing it away. For whatever reason, it's saying, hey, this check probably isn't important. So let's actually quit out of here, and let's compile with Clang++, vuln.cpp, and output it as vuln clang, just vuln clang. I don't think this will work the way I want it to, so let's run it, vuln clang. Okay, enter 9. It's still going to give us segmentation fault. We're still writing outside the bounds of what we want to, but let's actually now call this clang 03 and add optimization level 3 to this. And let's do the same thing. Let's do an ls-tech-l on anything that ends in .s. Or no, we don't care about that. Let's do an ls-tech-l. We can see the code size. Vuln clang 03. Now let's enter something outside the bounds, like 8, and it works, right? This might look like gibberish, right? It's 4 bytes of hex, hex 20, hex 7a, hex 6c, hex 70. Let's do the same thing for offset 9, same thing for offset 10 inside of our array. What is this? What's going on? Why does this look so janky? If we cat out secret.txt, we see it's please sub. If I do an xxd on it, we can see the actual hex bytes of it. So if I come up here and rerun this and do 8 again and do 9, we can see it's actually printing out the contents of our file, right? It'll be in little endian, so it's in reverse. So we see 70, 6C, 7A, 20, 70, 6C, 7A, 20. So that's how you can actually read outside the bounds of this array. And why does that work? I drew up a whiteboard diagram, and when I thought I was recording the video and I actually wasn't. So I guess this is just like me explaining it a little bit further in my horrible artwork. But essentially what we're doing is this. We have 2 buffers, right? We have array and we have secret. Let's just say array starts here, and it's going to start at address for simplicity, hex 1000. And that first element of the array is 0. And it's 4 bytes, or each element is an unsigned integer, which is 4 bytes in size. So at the next address, which is array plus 1, array plus, oh my goodness, array plus 1, which is actually array plus 1 times the size of your data type. And our data type is 4 bytes, so it's array plus 4 will be the next element, which is 1, and so on and so forth until we get all the way down to secret.txt, or that secret buffer. And let's make that a different color. Let's make it purple, because why not? Just like Barney. We have secret, And this will be at address hex 1032. It'll have P for police sub, and then secret +1. This looks absolutely terrible. I'm so sorry. This will be at hex 1036, and this will be an L, and so on and so forth. So now this time in red. So secret. So the base address of secret is actually array +8, because these are stored on top of each other on the stack. And since it is an unsigned integer, it's going to read 4 bytes. So in our case, we just entered ASCII strings, but it's going to read the first 4 bytes of what we have inside secret.txt. So hopefully that made sense. I know we did kind of a deep dive, and this wasn't really too much about the bug itself, but we got to learn a little bit about compilers and assemblers and preprocessors, and how 2 compilers that should be doing the same thing can have very different results. So when I browsed Twitter and I was looking at some of the other responses, a lot of them were incorrect. They weren't actually able to get it. A lot of people were hung up on this bounds check right here, index greater than or equal to size. Some people were saying, oh, just enter a negative number and you can do like some type of underflow. However, that's not going to work because it's unsigned. So a negative number is going to be converted to a big positive number. So if we look at unsigned integers in C++, we can see here, let me move this so you guys can see it. You can see here the ranges for a 32-bit unsigned integer is 0 to like 4 billion. So there you kind of have it. I don't think there's really too much else I wanted to showcase and discuss in this video. If we come back here to the Twitter thread and we kind of just want to poke around and look at what other people are saying. There we go. Yeah, there's a critical bug in the get element save function that allows for an out of bound reads, which can be exploited. And well, that's not true. There is no out of bounds read. This guy's saying, well, you wrote it in C. And C is a really great programming language. So someone said, hey, they fixed the bug. They added this additional check for if index is less than 0. But again, it can never be less than 0. So very interesting, pretty cool challenge. I went into a deep dive. I thought I could kind of easily solve it because we look at a lot of CTFs and C code and reverse engineering here. But it actually turns out the compiler that we were using either protected us or caused us to fail all along. So there you have it, folks. That's my solution. That's my write-up. That's my walkthrough for this video. Hopefully this was entertaining and enjoyable. As always, guys, if you enjoyed this kind of content, please like, comment, and subscribe. And as always, take it easy, and I'll see you in the next video.